Wait, are you in pineapple?
Good morning, happy Monday. Today we'll continue our discussion of self-energy, dipole self-energy, and how these concepts combine to predict intermolecular forces. And at the end of class on Friday, we talked about the self-energy of an ion and how we consider just a plain old ion not particularly high or low in energy, just kind of existing, doing its thing. But if we look at the matter closely and we subdivide a charge of some size, big Q, into the summation, the integration of an infinite number of infinitesimally small charges, Q, and we start with one little Q, then bring in another little Q, then a third, then a fourth, then a fifth, we can see that confining these charges to a small area actually creates quite a high potential energy situation. Yep.
Is that accurate to model that way? The charge is actually one
That's a good question. We know that even if it were, so the question was, since charges are quantized in units of the fundamental charge or thirds of charges if you want to deal with quarks, which you can if you want, but we're not going to. If you consider, the quick answer is yes, that conception of the world still does work, especially if you consider the fact that if you take charges that are not infinitesimally small, but charges that have multiples of the fundamental charge, so another E and another E and another E and another E, the argument works the same way, that confining charges, no matter how we just decide to subdivide them, still increase the electrostatic potential energy of the system. Now there are two ways, there are two the most common ways in which charges reduce their electrostatic potential energy, and one of them is by increasing the size. So delocalization of charges to get the infinitesimal pieces of themselves, in a way, as far apart as possible. So this explains for example, from chemistry, as you take HF, then HCl, then HBr, then HI, the acidity goes up as you go down the periodic table in group 7 of the periodic table. And the reason is because the conjugate base is more stable. Anyone remember that? Now, why is the conjugate base more stable? It's because the conjugate base is bigger. It's because it has reduced its electrostatic self-energy by being bigger, by having that negative charge delocalized over a larger volume. The other way in which charges and dipoles of all types reduce their electrostatic potential energy is by associating with charges of the opposite type. And that serves to satisfy this kind of pent-up high potential energy, this instability. And if something comes close to it, say it's a negative charge and a positive charge comes close to it, the electrostatic self-energy is used up in its interaction with this, and that's good. That lowers the overall energy of the system. So if you think about a dipole, which is, in this simple conception, we just take two ions and put them into contact with each other, and the center-to-center distance is little l, and the radius is a. So in this case, L is equal to 2 times A. And we'll just say that the radius is the same, even though I didn't draw the circles the same size, but that was an accident. And if we look at the self-energy of the system, we see that the work done to create this system is equivalent to the electrostatic self-energy. So first, we have two unfavorable positive contributions due to the fact that we created these two charges. Then we're lowering the potential energy by considering the fact that two of these charges have been brought together from an infinite distance, which serves to lower the potential energy. So in the end, we still have, if you use this substitution and you do some algebra, you end up with the dipole moment squared, which is defined as the partial charge times the length between the partial charges over 4 pi epsilon naught, which is the permittivity of free space. It's a constant times the dielectric constant of the environment. In the case of vacuum or air, it's 1, or pretty damn near 1. And then L cubed, which is just the separation cubed. So what we're going to find is that the interaction between not only molecules, but also nanoparticles and colloidal suspensions and a good chunk of the systems that you're going to find in nanoengineering and chemical engineering and formulation science is dependent on attractive forces due to the lowering of potential energy due to confined charges and dipoles, combined with 1 or 2 other forces that serve to push the particles apart. So this is the basis of the Van der Waals force, this concept of lowering the electrostatic potential energy. And then we have other forces in real systems that serve to push particles farther apart. And we're going to spend this week talking about these types of intermolecular first, and then we'll sum them up to get interparticle forces. And that will be the end of the first of 3 units, and then the exam will be next week. Okay, so what we're going to do is build up the Van der Waals force. And we talked about this the first or second day of class, but I want to give you a little bit more detail as to what's going on. So let me give you the high level overview. There are 3 components of the Van der Waals force. There's the dipole-dipole force, which is sometimes called the Keesom force after the discoverer, Professor Keesom. Then, and what is the dipole-dipole force? You have 2 dipoles that, if they're infinitely separated apart and there's some energy in the system, they just rotate they rotate with random orientations. As you bring them closer together, the dipoles produce electric fields which can serve to align the dipole nearby. So in some orientations, say my index finger is the negative side and my thumb is the positive side, and same thing on my right hand, there will be some orientations where the positive or the negative end of the dipole serves to orient the other dipole in some in a way that reduces the electrostatic energy of the system, and that will produce an attractive force. Incidentally, this situation is electrostatically unfavorable, so this orientation will be statistically less likely. So you have these rotating dipoles, but it's sort of in this kind of configuration where they're more or less aligned in the same direction, and that alignment and the force that the alignment produces gets greater as the separation distance decreases. So we can represent this as follows. So the dipole-dipole force, sometimes called the Keesom interaction, has 2 molecules, and we will represent the dipoles. This is just a snapshot of one possible configuration, and we'll call these, they're freely rotating. They're not free with respect to each other, but they're free with respect to external constraints. So we're not saying one is absolutely fixed, like it might be in a biological structure where where the dipole is bonded to a protein, or the dipole is part of a protein, and it's fixed there and it's not going to move. We're saying that these are these dipoles are not tethered except to the electric fields that each other produces. So these are freely rotating, and I'll put freely in quotes so that you know that the caveat is that they don't have random orientations, their orientations are affected by the nearby dipole. Freely rotating. And what we have is our transient orientations of speaking. We're going to speak about the system from the perspective of U1, of molecule 1, dipole moment 1. So transient orientations of U1 produce an electric field which serves to align U2 transiently. So some orientations of U2 are more probable than other orientations. And if you consider the potential energy, this is the work of bringing two molecules together with all the possible angles averaged. This is the angle averaged the angle averaged potential energy of this interaction ends up being, it's a form that looks a little bit like Coulomb's law, but we're talking about dipoles instead of individual charges. We have minus U1 squared, U2 squared over 3 times 4 pi epsilon naught epsilon squared times the Boltzmann constant times the temperature r to the 6th. Now the factor of the 3, the kb, and the t come from, I'm not going to derive this because it would take like 20 minutes to do, but it's not really that ridiculous in principle. But the 3, the k, and the t come out of an angle averaging process where the distribution of the angles of one freely rotating dipole with respect to the other influence the allowable orientations of the other. This is how we know, one hallmark of the Van der Waals forces is that they're dependent on r to the 6th. It just kind of happens that they all have this dependency. So Van der Waals force is dependent on 1 over r to the 6th, where r is the center-to-center distance between the molecules. The dipole-dipole force is the only one that's dependent on temperature. At really high temperatures, the dipole-dipole force goes away. Now, why would that be? The dipole-dipole force, it depends. Say you have a really high temperature, then you're giving these molecules a lot more freedom to rotate, and they end up carrying less. If you have more thermal energy available, you can sort of break the spell. One molecule can break the spell of the other molecule so that they can both rotate more freely. That kind of makes sense. They can break out of the hold of the electric field of one of the molecules, of their interacting molecule. Okay. How about the dipole-induced dipole, or Debye interaction? In this case, what we have is the dipole moment of a polar molecule, U, interacting with, so this is a polar molecule, and this is the electron cloud of a nearby molecule. And again, the center-to-center distance is r. So this is a freely rotating dipole interacting with the electron cloud of a nearby molecule. Freely rotating dipole polarizing the electron cloud of a nearby molecule. Polarizing transiently. To form an induced dipole. So imagine now we have a similar situation to over here, but except we take the U2 and it's just the electron cloud of a nearby molecule. But it turns out we get a similar type of interaction. If you have an electron cloud, an electron buzzing around a nucleus, and you take a dipole that's oriented with its negative side toward the electron cloud, the electrons are mobile, but the proton is not. What's going to happen? The electron density is going to shift away from the negative end of the dipole. Then there's going to be, so the proton is here, the electron cloud is here, the electrons are going to shift away and form a dipole. And that dipole is then going to be attracted to the negative end of the freely rotating dipole. And once you model, and I should say, what is, I'll say that in a second. We have U squared alpha, and I'll say what alpha is in a second, over 4 pi epsilon naught epsilon squared times r to the 6th. Alpha is called the polarizability, and it is the strength of an induced dipole given an electric field, capital E. So this is the strength of an induced dipole in the E field. This is the polarizability. And again, we have an inverse r to the 6th dependence. No temperature dependence here. Yeah. The question is it more favorable for the positive end of the permanent dipole or the negative end of the permanent dipole to polarize the electron cloud? In principle, it makes no difference. Of course, it will be polarized in the opposite direction. If the positive end is facing the electron cloud, so that's my thumb, I guess, then the electron cloud will be shifted toward the positive end. Okay, the third and final is the is the dispersion interaction, named after the town it was discovered in. Just kidding. London was a dude. And in this case, we have two electron clouds interacting with each other. Now, why on earth would two electron clouds interacting with each other produce an attractive force? Well, because the electrons actually, while we consider them as quantum mechanical objects that exist in these orbitals that are both point particles and existing everywhere simultaneously, they actually do have an orbital frequency, and in some sense, they behave particle-like. Some manifestations of the behavior of electrons are particle-like, some of them are wave-like. In the conception of the dispersion interaction, we can consider them that they actually do, well, you can sort of consider it as delocalized or localized to particles. And the way you might consider it in the case where they are particles is that one electron is zooming around its orbit, and in some cases, there will be a dipole which is more or less randomly oriented depending on where the electron is relative to the nucleus, and that a snapshot at any given time will have a dipole. There will be a dipole which, just like the other two interactions, will produce an electric field that serves to align a dipole in an adjacent molecule. In this case, the dipole in the adjacent molecule is made up of the electron orbiting the nucleus. So some regions of space, you're going to be more likely to find the electron in some regions of space depending on the electric field produced by this other electron orbiting around a nucleus. The other conception is just to consider the electron as a cloud, not as a point particle, but a negatively charged cloud that is mobile. It's sort of mushy, kind of mushy. So if you bring two electron clouds together, the electron clouds are mushy, but the protons in the nucleus are fixed. The electron clouds are going to want to push away from each other, almost like static electricity. Pretty much exactly like static electricity. But because there is some transience of the polarization, it's not going to stay like that forever. There's going to be some quantum mechanical forces that force the electron in one molecule to go back, and you're not going to have just this permanent repulsive induced dipole. So it really does. It's really important to keep the conception of an orbital frequency and the fact that the dipoles are never going to be exactly fixed. So what happens is that electrons buzzing around here, transient dipole produces a dipole on the adjacent molecule, and in the statistical in the high probability that they're aligned as opposed to anti-aligned, there will be a repulsive or an overall attractive force. So the electron clouds of two molecules interacting with each other you have a transient dipole of one produces an E field that polarizes the other. The transient dipole of one molecule produces E field that polarizes the other. And what does this look like? the interaction potential energy is minus 3/4 times the polarizability squared times h nu, and I'll tell you what that is in a moment, over 4 pi epsilon naught squared r to the 6th. We're going to consider the case of a vacuum only. So we don't have we're going to assume that epsilon is 1. So the reason we're doing this is because it becomes 1,000 times more complicated if we're doing this in a medium. But on Wednesday we'll talk about ways in which it doesn't matter because the values for any material you're likely to find have already been tabulated. I just want to show you how this works. So h is Planck's constant, and nu is the orbital frequency of the electron. And the orbital frequency of the electron is somewhere around 3 times 10 to the 15 per second, or hertz. We also assume that the electron clouds here have the same polarizability, which they don't necessarily, but in the case where they're the same molecule, they do have the same polarizability. Yeah. So that is all. So the question is, the bigger the electron cloud, the bigger the induced dipole, because we have dipole equals Q times L. And the size of the dipole, or the size of the electron cloud, is all manifested in the polarizability. It turns out that the polarizability is approximately goes with the square of the volume of the molecule. So we won't derive the polarizability. In 1 or 2 years, you can take my class NANO 202, which is a class on intermolecular and surface forces, and we'll derive where the polarizability comes from.
How does it measure that frequency of the electron? Is it really just a full rotation on the cloud?
By the Bohr, so the question is, how do you measure the rotational frequency of the electron? The short answer is I don't know, but given the allowed orbital energies from quantum mechanics, you can calculate the frequency given a mass of an electron. But the conception of, so in the Bohr model, it's literally the frequency that it takes the electron, the frequency of rotation of the electron about the nucleus. The real system is more like, and the real system is the real system is more like, how's that go again? One more time for emphasis. Okay, so the total Van der Waals force W of r equals 1 plus 2 plus 3, 1 which I erased because I hate it, 2 plus 3. Just kidding, I don't hate the Keeson force. And this is minus some constant, some Van der Waals constant over r to the 6th. So what is the Van der Waals constant? Well, the Van der Waals constant is all this junk plus all this plus all this over the common factor of r to the 6th. So the C dispersion is the C Van der Waals is the C dipole plus the C dipole induced dipole plus the C dispersion. So each molecular interaction has its own set of C's. And each molecular interaction, more importantly, has its own C Van der Waals where somebody has already done the calculation or the measurement in the lab. And you can actually measure these. You can actually measure these forces in the lab, and it's particularly easy to do if you have. Well, it's never easy to do, but it's more straightforward to do if you have macroscopic particles that are actually made of these molecules. Okay, a couple of comments about these. I mentioned that the dipole-dipole force, the Keesom force, is the only one that depends on temperature. And that's because there's going to be a distribution of angles between U1 and U2. But the more energy there is in the system, the more thermal energy there is in the system, the broader that distribution is going to be, because it's going to be easier for one to break free of the hold of the other, of the field produced by the other. Is that okay? We think of the dispersion force as kind of a weak thing, like, yeah, electrons making dipoles, yeah, that's going to be strong. But it turns out that for molecules of appreciable size, so molecules appreciable size and dipoles that are not that strong, which turns out to be most molecules you could possibly think of, or most materials you could possibly think of. And by molecule, I mean anything from like some drug molecule to a gold nanoparticle. I'm using the word molecule in a very loose sense. Some angstrom to nano-sized object, or actually macroscopic objects as well. The dispersion interaction for most real matter is actually more important than the dipole-dipole and dipole-induced dipole forces, especially for molecules of appreciable size with moderate dipole moments. So amino acids, where you have formal charge on one side and unformal charge on the other, sure, Keesom is going to be higher for that. Or for water, it's going to be higher for that. But even, because of hydrogen bonding, but even small molecules that have hydrogen bonding, even small molecules that have hydrogen bonding, the dispersion interaction is actually greater. Like ammonia, which is just NH3. Dispersion interaction wins over the others. Yes?
Can you explain that as because of the that problem that you're demonstrating earlier, that random nature of the front motion, is that just a more active force than, say, a dipole?
It's because every time you add the dipole moment it's more of a size argument than anything else. The more, it's hard to increase the size of a dipole by very much. You can have a couple of dBi, which is the unit of a dipole moment. You can't get 100 dBi very easily, or 1,000. Usually 1 to 5-ish. Whereas in the dispersion force, you add, say you have methane versus octane. You've multiplied the number of dispersion interactions by more than a factor of 8 just by increasing the size of the molecule. And it's the interaction with molecules other than its nearest neighbor. So it's mostly a size argument, but they actually start out on similar footing, but then it's much easier to increase the dispersion interaction than it is to increase the dipolar, the ones that require a permanent dipole. Let me write down these points. three main takeaways, the three takeaways I have on this. Dipole is temperature dependent, and it's the only one of the three that's temperature dependent. Dispersion dominates for most species of appreciable size. Unless you have just a ridiculously strong dipole in a small molecule. And the third point is that because of the quantum mechanical character of the dispersion interaction, it actually goes away after a certain distance. The reason it goes away is as follows. Electric fields, or electrostatic interactions are mediated by photons, mediated by by EM waves that travel at the speed of light. Because we have a frequency of the electron, which is 10 to the 15 per second, it might be that we get to a certain distance of separation, and the orbital frequency of the electron doesn't give enough time for the other molecule to react. So the dipole moves over here to over here, and then it sends a photon. In Game of Thrones, this would be it sends a raven over here, and then the electron cloud responds or doesn't, or it responds in some way. But by the time the molecule reacts, the electron in the transient dipole over here might be in a different place. So it turns out that after a few nanometers of distance, the dispersion energy starts to go down, and at about 100 nanometers, it's gone. Yeah, let me write this down first. So dispersion energy disappears for R greater than approximately 100 nanometers because of finite speed of light. In contrast, the motions that give rise, the molecular motions that give rise to the transient dipoles of permanent dipoles, the orientations of permanent dipoles occur on a much, much slower time scale than this, and the speed of light doesn't, for our purposes, doesn't matter. So the question is, why aren't the other two dependent on temperature? And the reason is that the electrons are still moving about the nucleus at absolute zero. So the electronic motion is not affected by temperature, and it's the motion of the electrons is manifested in the alpha parameter in both the dipole-induced dipole and the dispersion force. They don't depend on temperature. Neither. Yeah.
You described temperature dependence as being affected at high temperatures. So, of course, at absolute zero, it wouldn't affect the dipole-dipole interaction either. So why at high temperatures would dipole-dipole break down with these synthesis?
So at so they persist. They're easier to break, but the force is still present. So at high temperature, you have a lot more energy to break Van der Waals bonds, but the force is still present. In the case of the dipole-dipole interaction, you're deleting the force at high temperature. Right. Okay, let's add up all of these forces to talk about how actual nanoparticles and matter interact with one another. Van der Waals forces between surfaces and particles. So imagine a molecule interacting with a surface of like molecules by W of R equals minus C van der Waals over R to the 6th. So here is our molecule. Here is our surface of like molecules. And we'll call this the z-axis, where this is the molecule here is interacting with this surface of like molecules. And we'll call the distance between the surface, the molecule and the surface D, capital D, instead of R. So R refers to molecule-molecule interactions, and we're going to use D for the distance between macroscopic objects. In this case, it's a molecule and some macroscopic object. So the distance here, the absolute distance of this line segment is D. This is the z-axis. And what we're going to do is consider, we're going to integrate the interaction energy between this molecule and every molecule on this surface. And how we're going to do this is consider annular rings starting at the center. They get progressively bigger, then they move further into the depth and get progressively bigger, then they move further into the depth. The 5 minutes left. They get further into the surface. So what do these annular rings look like? I'm going to have to ask you to use your imagination through my crappy artwork. But imagine that these are rings that go further into the surface, that have a cross-section, a square cross-section with area dz, dx. And what we have is a volume of the ring equal to 2 pi x dx dz, where 2 pi x is the circumference and dx dz is the area. And the number of molecules in this infinitesimally small a volume element is rho times 2 pi x dx dz, where rho is the number of molecules per unit volume. So the net interaction energy we'll call it big W of big D is the double integral of minus C Van der Waals over R to the 6th times rho 2 pi x dx dz. Forgot something here. The distance here between this point and the infinitesimal volume element by Pythagorean's theorem is z squared plus x squared under the square root. So we have this double integral equals minus 2 pi c rho, because all this stuff is constant, times the integral from z equals d to infinity into the bulk of dz times the integral from x equals 0 to infinity, that's up and down, of x dx over z squared plus x squared cubed. Evaluated, once you look this up in a table or do it in Mathematica or whatever, you get minus pi, and you won't have to do any of this for the homework, don't worry about that. Just want to show you the result is minus pi c rho over 6 d cubed. And I want to end by saying, and we'll start here next time, I'll just draw this out and we'll talk about it some more next time, is that the force, this is the energy, but the force has a relationship with energy of the negative rate of change of the energy with respect to distance. So the derivative with respect to d is minus pi c rho over 2d to the 4th. And before I let you go, I have 30 seconds left. This is very important. The difference between force and energy, how an energy being negative or positive doesn't really matter so much as the rate of change in going from something that's far apart and something that's close together. If you go from high energy here to low energy here, the force is negative and attractive. If you go from high energy here to higher energy here, it's repulsive and the force is positive. So remember that the energy does not have a physical manifestation, only the force does. I will see you on Wednesday, thanks.